Let's continue. Switch to blue. Number 4. All right, here we go. Again, before we even look at any other information, we're going to look for the equation. We're going to write the equation, the expression, all of that lovely stuff. So it looks like I've got an equation over there on the far left. It says 2NO, 2H2. Looks like they're all gases. Our K expression then all right, so let's do our ice information. Okay, first it says a mixture of a bunch of stuff is placed in a flask, and then we're given an equilibrium value. So is this stuff initial or final? Initial. This is all initial, right? And it's a 1 liter flask, so even though we're given molar amounts, we can put them into molarities, right? We'll just say that whatever their molar amounts are is molar. So 0.1 moles of NO. Sorry, 0.05 moles of this, and 0.01, sorry, 0.1 moles of this. Then we're told the equilibrium concentration of NO is 0.062. My goal is calculate the equilibrium concentrations of everything else for part A, right? So we want to figure out what all these values are going to be. Am I going to need change values here? We weren't told this one, so we're just assuming it's 0, right? Change values are absolutely necessary. So on the left side, what am I going to write here? Minus what? X or 2x? 2x.
Wait, why?
Because there's a 2 in front of the NO.
Okay. How much is that?
Huh?
How much is actually changing?
We're going to get there. Okay? What am I going to write here?
Minus 2x?
Minus 2x. Am I going to write here? Plus x. What am I going to write here? Okay, I am going to continue by dropping everything down. Now I have expressions for K, or expressions for the equilibrium. For my particular cases, this looks like a nightmare to plug into my K expression and try to solve for X. Okay? There is a shortcut in this particular problem. Do we know X because we were given this information? Can we calculate X if we just plug this minus this equals this? That's exactly what had to have happened. And whatever that change is going to apply everywhere else by definition. Do you see why? Okay. This is a very unique situation. You have to have all 3 given at the beginning of a problem in order to do this. If you are not given this, you got to plug it in and do the whole quadratic equation, quartic equation, cubic equation. Yes?
Where do the numbers in the second row come from?
Those are our changes, so we don't know what the changes are. We just know that they are going to be molar equivalents. So that's where we get the 2, because that's what's the coefficient. And we know that whatever this changes has to be 2 times whatever the change over here is going to be. So we use molar equivalents in this particular case, but coefficients, if you will. Okay? All right, what'd you get for X? From there, what do? Plug and chug, get the equilibrium concentrations of everything, and then get a K value. Part A says, what are the equilibrium concentrations? Part B says, what is K? And it says KC, so you don't have to do the conversion.
Did you just use the .062 for your first one?
Yep, you already have the equilibrium of the first one. You need these ones. So this one, woo, that was easy. Because it's just X.
Harvard is calling you.
You're busy.
Harvard, Illinois.
You're busy. What's up?
Is the X and the C row also like 0.019?
Yeah, X is in general 0.019. Plug it in all across. Get your equilibrium concentrations. Yes.
For the 2H, I have .012.
For which one?
For the 2H2.
Did I do something wrong? What'd you say?
Wait, what?
.012.
Yeah, that's what I
Yeah, that
got
makes
too.
sense. You're fine. I think this number's wrong. Look. Yeah, they did it on my iPhone last night. Like, I'm tell me that. Just saying. This is why you shouldn't do stuff on your phone calculators, guys. Okay, the bigger number. Yes, Ryan.
Is that it?
Minus 2x. 0.05 minus 2x should be 0.012. You got it right there. It's not 0.03. X is 0.019.
Oh, okay.
You multiplied it and then you multiplied it again. Too many multipliers. Should have gotten a K of about 653.
I was concerned because it seemed a little.
Nope. Move on to number 5. Start setting up number 5. Get your expression written. Get your ice table made. You can do it. Say again? Yeah. Almost Valentine's Day.
What?
It's almost Valentine's Day. first question asks you what are the pressures of each of the individual things. You are given molar amounts in the equation, right? You're given how many moles of each thing there are. You're told what the temperature is, so T. Are you given volume?
Yes.
You are given volume. Can you calculate pressures of each individual thing? Yes, you can. Yes, Emma?
So, is that what we do? I thought you would divide the amount of sequence by 2.
Because it's a 2-liter vessel, yeah, so that'll get you N over V. But now we're trying to get everything into pressures first.
To put it, okay.
Because our first question says, what are the pressures? The second question says, okay, now everything is given in pressures instead of concentrations. And remember that when we talked about this, Kp and Kc, the only difference is one uses concentrations, one uses pressures. So we can say that the K expression, this one in particular represents concentrations, but isn't Kp the same exact thing, just pressures instead of concentrations? So that's where we're going, is we're trying to use pressures instead of concentrations in this one.
But when you're putting in like initial in your table, you're just gonna take what it gives you divide by 2, right?
Not quite yet. No, we're gonna use pressures that we calculate in our initial change and equilibrium. Because that's why it wants us to start this problem by calculating pressures. Because look, it says calculate pressures, then it says at equilibrium you're given a pressure, so calculate the equilibrium pressures. So instead of doing everything in concentrations, we're gonna do pressures instead. So in order to do that, we have to calculate our initial pressures using the PV equals nRT.
What's the R value again?
0.08206. Yes.
So for the N, you would take what they're giving you? Or would you divide that value by 2?
The V is 2.
Alright, so it's just liters.
So you do divide.
You're not, yeah, so you're going to divide this whole thing by 2.
So yeah, so to answer the question, yes.
Kind of, yes. She's asking because she wants to keep it in concentrations and I need you to calculate pressures.
No. I got it.
Okay,
I don't.
so N is going to be what value? So let's do CO2 first. Okay?
That would be
How many moles of CO2 are there?
0.
0.2. We're going to divide that by the 2 liters. Then we're going to multiply by the 0.08206 in the temperature, which is at 500. Does that make sense? Yeah.
Yeah.
I have the answer.
What is it?
4.103 ATM.
Okay. Keep going. Get the next pressure. Pressure of H2. Okay, so A was to calculate the 3 pressures. Now, those 3 pressures are all based on what kind of information? Initial or equilibrium information? Initial. So we're going to put the pressures in our table instead of concentrations. Because our goal instead of Kc is Kp. And remember that the only difference is that we're going to use pressures of the things instead of concentrations. The expression is exactly the same. We're just going to put different data into it. So I'm going to take my initial pressures and I'm going to put them into my table as initial information. Okay, so there's that. What other information was I given in part B? The pressure of H2O at equilibrium is 3.51. Where does that go in here? Yes?
We assume that CO is zero.
Yes. Remember, if you're not given it, you assume its initial concentration is not present. Good catch. Okay, so do we need to use the change table at all?
Yeah.
We kind of do. We want to fill it in, right? What are we going to put here on the left?
Minus X.
Minus x. This one?
Minus X.
Over here?
Minus X.
On both of them, right? Now the next step would be to just drag them all down. 4.1. Okay. Here's the thing. We already know this. Remember that trick we did last time, right? Can't we use the same trick? We absolutely can. If we can figure out what x is, then we just have to plug it into everything else. So we can solve this expression, this plus this equals 3.51, to get what x is. Now on my equilibrium tables, one of the things I want to point out is if you try to do this with any other one of these, you're going to get x on both sides of the equation. You can't really solve that. You should have a number on one side, x on the other side. So just kind of keep track of that. All right, what do we get for x?
22,276.
Sure. Okay, what do I do with it? Plug it back into our equilibrium, get our equilibrium concentrations. These are pressures. Sorry, equilibrium pressures. I got 1.824 here, and I got 3.875 here. All right, so here are our equilibrium pressures. Part B also says, Part B just says to calculate equilibrium pressures, so that's good, right? This was B. Part C says what is Kp? So what are we going to do? Plug it into the expression and get a Kp value. So remember, this is my expression. Yes.
How did you get it? I think the value for the E for the CO2 is, I think it's 3.6.
So you do 4.103 minus 0.22.
I have a 2x there.
Nope.
Okay, that's why.
I keep trying to rewrite that number and I keep failing. All right. Did you get that value for Kp? Okay. My next question is, product or reactant favored? Reactant favored, less than 1. Close to 1, but less than 1. Reactant favored. So when we go to convert this from Kp to Kc, should the reaction still be reactant favored?
Yeah.
Absolutely, it should be. But we're in really close territory. All right. Our last one brings back an oldie but a goodie from the beginning of this chapter, converting Kc and Kp. So how do we go from Kp to Kc? We use that equation. RT to the delta n. What's delta n? 1 plus 1 on the right, minus 1 plus 1 on the right, on the left, so 0. So what does that mean? This becomes, oops, not 0, 1. Anything raised to the power of 0 is a 1, right? So
KC.
KP and KC are equal to each other. Okay? New application equilibrium. I know the pressure thing can be kind of confusing. All right, let's do the last one. This one is based on that Q argument we discussed. Okay, so we're going to start it the exact same way. You want an equilibrium expression. Okay, that's the very first thing we want. We can write out the equation and put in the ICE table. You're going to see you don't need it, but you're welcome to do so. For all of the different equilibrium problems, please make sure you start them all the same way with an expression and an ICE table. ICE tables are your friend. You will be using them a lot. Not just this chapter, the next 2 chapters as well. All right, here we go. The equilibrium constant for the reaction has a value of Kc equals 2.19 times 10 to the negative 10th. The reaction is this, which means the expression is this. Do you agree? Products over reactants raised to their powers. Nothing has a 2 or a 3 or anything of that nature. Okay. Now, the next part of the reaction says, are these at equilibrium? If they are not, which direction do they need to go? If it asks you, indicate the direction it must proceed to reach equilibrium, it wants you to measure Q and compare it to K. So we're going to use the given concentrations and we're going to plug them into the equilibrium expression to get a Q value. Remember that the Q expression is identical to the K expression. We just need a number for Q to compare to the given equilibrium constant. So let's do A. Plug in given numbers in the right places. You're going to get please make sure you put parentheses around these numbers. They're small. What'd you get?
1.0923 times 10 to the negative 8.
Nice. What does that mean about Q compared to K? Bigger or smaller?
Bigger.
Bigger. Thinking back to what we said in lecture. Yep. Because K is a smaller number. The exponents are negative. When Q is greater than K, which direction does the reaction need to shift to get to equilibrium?
Towards the reaction.
To the left or towards the reactants? Good. Do B. Oops.
Why reactants go on top?
Hmm?
Am I mistaken?
What?
Oh, no. Okay, I'm being stupid.
Doing the same thing with new numbers. Okay?
Oh wait, how do I get to the 11? Oh wait, that's a 7 there? Okay, never mind, I got it. Six.
What does that mean?
You're on the negative or right.
It has to shift to the right to get to equilibrium. Okay? So Q again, great indicator of where we're at versus where we want to get. But you need to remember Q greater than K means get to the reactants. Q less than K means get to the products. Q equal to K means you're at equilibrium. And is also rare, if not, never happens. Okay? All right. You now have done a lot of problems. Your homework or problem set, it is not homework, I'm sorry. Do not do it for homework. The problems that are in that document that come after this say, your turn. You're going to work on this in class tomorrow as well. Okay? You do not finish in class tomorrow, it will be homework.
I thought you were about to say right now.
You do not finish in class tomorrow, it will be homework, but please do not work on it for
First the
homework
total
tonight.
is 11.
So that way as you work tomorrow, you can check your answers, because I do not want you to get them wrong and think you've done them all correctly. That sucks.
So much confidence in them.
Why 11 though?
What?
I said, why 11 though?
Used to be 15.
15's a much
Seems
better
like-
number. You're giving us 15. 15's a better number.
Really, the fact I have to drive 4.
Why 11? You do it on the test. I